All right. So we finally move on to the top level of the memory architecture um, of shared memory, right? How we could optimize or improve or make sure our shared memory access is optimized, right? The technique, actually just one technique, and the only problem we need to avoid is called the bank conflict. And in order to avoid that problem, a technique is called the memory padding. Okay, right. So let's see what is bank conflict. Okay, all right. So again, the hardware architecture of shared memory is different from global memory. So that's why, in order to achieve his highest memory access time, it has a different memory access requirement, or uh, different different requirement, different constraint. And for shared memory, it doesn't require the memories to the memory access to be consecutive or sequential access. However, it needs to avoid bank conflict. So what is a bank conflict? So for shared memory, it's consists of many banks. Okay. For example, here, this is just an example. So usually it's more than 60. Usually, I think 32 banks. Okay. This is just a small example. So let's say the shared memory consists of 16 banks. Okay. And each bank will store usually is 4 bytes of data as a unit to store the data. Okay. So your data, when you write it to shared memory, is actually striped across those banks. So for example, say you have 62 elements integer array. So every integer, let's say, is 4 bytes. So the first element of your array will be stored on bank 0. The second element of the array will store on bank 1, so on and so forth. And after you reach bank 15, then the 16th element will store on bank 0 again. So it's stored on those banks in a round-robin fashion. Okay, so your data is striped across those banks. Okay, all right. So for each bank, you actually can store many data, right, or many data elements. Okay. However, each bank has its own access channel. Okay, so when you read the data, if the data is they are on different banks, then those requests, those memory access requests, can be handled concurrently through different channel across those banks at the same time. So it can maximize your bandwidth, right? Of course, if you can read, if your data is striped across all 60 banks, and you write one element from each bank at the same time, then you can fully utilize the bandwidth from your computing core to the shared memory. Okay. However, on the other hand, if the data you try to access, they are located on the same bank, then unfortunately, maybe those data access is issued in parallel by different threads. But because the data is stored on the same banks, you have to access the data or read the data using a single channel, the same channel. So that means the data access on the bank needs to be serialized because each bank only has one channel, right? So if you have data access occur on the same bank, is what we call the bank conflict, right? You have confliction on the same bank. And the result of that is a serialized memory access on those memory access requests. Okay, so you have to serialize the access. So of course, you cannot fully explore the bandwidth, and even worse, they are serialized. So the latency, of course, will be longer. Okay, okay, so that's why it's so important to avoid a bank conflict. Okay, and usually it does affect the performance a lot. Okay. So again, how to avoid that is through controlling the memory access pattern. And the pattern, right? Any pattern can avoid bank conflict as long as they don't issue the request to the same bank at the same time, right? So some of the pattern that can guarantee without bank conflict is, for example, the linear addressing, right? Because if within a WAP, again, we only consider the access from a WAP, right? Those threads can access has a linear addressing across those threads, means the data is linearized on the shared memory. So of course they will stride across the shared memory, right? So if you have 16 threads and you have 16 banks, then of course there will be a one-to-one mapping without bank conflict. So linear addressing can always minimize bank conflict, but sometimes you don't need linear addressing to avoid bank conflict. As a matter of fact, you can have any access pattern without as long as they are one-to-one permutation, then you won't have a bank conflict. Okay, for example, over here, right, you can see that every thread, the memory access pattern is very complex, or they just mix up across those threads. But from the memory bank point of view, each bank still only accessed by one thread. So that means there is a one-to-one permutation from the thread to the memory bank. Then there's no bank conflict as well. Okay, so it actually allow many other pattern. Okay, but usually, of course, the regular way, the standard way is to ensure linear addressing. So you can avoid bank conflict as much as possible. Okay. All right. So another special case without bank conflict is it happens when if half of WAP, the threads in half of WAP, they access the same bank, but they are only trying to read the data out from the same data on that bank. In that case, the hardware has a built-in optimization to support the broadcast mechanism, so that you can imagine what happened is the shared memory controller will simply just broadcast this data to thread 1 to 3. Okay, for example, here the WAP size is only 8, so you can broadcast the content to thread 0 to 3, which is a half WAP, right? So even though they try to read the same data from the same bank, it seems to be a full-way bank conflict in the worst case. But because of this optimization support from hardware, then so it won't cause any bank conflict as a result. Okay, this arrow should move down a little bit. Sorry about that. This arrow should point you to bank 2 instead of bank 1. Okay, so that there's no bank conflict. So for the rest of the WAP, right, you can see that for thread 4 to 7, they pointed to bank 2, 4, 6, 7. So they pointed to, again, different banks. So there's also no bank conflicts happen for the second half of our WAP. Okay. All right. So it's a special case. So if happen you have this pattern, then you can also avoid bank conflict. Okay? So there's only a couple of cases can guarantee no bank confliction on your shared memory. Okay? All right. So just another example. So here you can see we can just simply look at the plot instead of look at the code, because the plot illustrates what happened to the code. So simply put, in this case, we have 64 threads operate on shared memory with 32 banks. Okay, and the access pattern, if you just trace the code, then you can you can find out how the thread will access each of the bank. Okay, and because this is arrays, actually you can see it's a 2 by 32 array. Okay, so you have 64 elements. Okay, and when we write this, unfortunately, the way we write this is will cause a two-way bank conflict. Okay, means that for every bank there is have two threats assets at the same time. So that's why it's called the two-way bank conflict. If you have 32 threats assets a bank at a time, then it's called a 32-way bank conflict. And of course, the more, right, the larger the number it is, the worse the performance, because it will serialize all the requests on that bank. Okay, so this is an example that will create a two-way bank conflict. Okay, so you can imagine it is possible to rewrite this code, okay, to avoid two-way bank conflict. Okay? If we place those data on a different position of your shared memory, right? Try to spread out the data, right, to across all 32 banks, then it is possible to rewrite this code without bank conflict, right? So you can, of course, go back and think about it as a practice. And of course, for your homework, you also need to check your memory access pattern to make sure there's no bank conflict. And if there is, you need to think about how to maybe to reorder the data pointer of each thread, or try to rearrange your array on the shared memory in order to avoid bank confliction. Okay. Okay, so in general, how to avoid that? First, try to have a linear addressing accesses, right? Don't try to have a stripe addressing like this. This is striping because it jump every two element, right? So if we could access in by by a step of one, it is possible to avoid bank confliction. Okay. However, if this cannot resolve the problem, then another solution is called the memory padding. Okay, so let's see what's memory padding. Okay, okay. So the example we use actually follow the transport example we introduced before when we talk about the closest memory access on global memory. If you remember at that time, right, we try to read out the data from shared memory in a column major and write it out on global memory in a row major manner. Okay, so we say supposedly shared memory can, without any bank conflict, if you are, read or write the data in the column major, because as long as they don't have bank conflict, right, then the performance, the bandwidth, the bandwidth can be fully utilized. Okay? However, if it's happened that in this case, as you can see, let's say the matrix is happen to be a 32 by 32 matrix, and the banks we have on shared memory is also 32. Then what happened is the color here indicate which bank the data element is stored on. Okay, so that means as you remember, right, the shared memory, the data of your shared memory is will be linearized and linearized on the shared memory space in a row major fashion, right? So what happens is the first element, the first row of the first column will be stored on bank 0, and the first and then the second column of the first row, because it's a row major, so you will store on bank 1, so on and so forth. Okay, and after 32 element, we we roll it back, and then so for the second row, again the first element will be placed on bank 0, so on and so forth. Okay, so you can see that it just happened that for all the elements for the first column will be on bank 0, right? Will store in bank 0, and the second column color in color in red, in red color, will be stored on bank 1, and so on and so forth. So it's happened that every column will be stored on the same bank in this case. Okay, so if we try to read the data from the shared memory in a column major way, then that means for the WAP, right? For a single WAP, the first thread will read this element, the second thread will read this element, right? So on and so forth. And you can see all the threads. If say we know 32 threads, right? 32 threads within the WAP, then those 32 threads, well, if we read it in column major way, then all the threads within the WAP will read the data on the same bank, on the same color, right? Clearly, right? So that means you have a 32-way bank conflicts, the worst case you can have in this situation. Okay, so actually the solution we introduced before, although it optimized for global memory, it's not completely optimized for shared memory yet, because it has a 32 bank conflicts on the shared memory. Okay, all right. So how to solve that, right? And the one way to solve that is things with our data is already placed on shared memory. So, and we have to read it out in the column major manner. So all we could do is try to figure out how could we, right, interleave the data on the banks, right? So that you can see in this case, for every column, the element will also stripe across different banks, right? They have, if they are colored in different colors, then that means they are located on different banks. So when we try to read out the same column at the column at the same time, they will be located on different bank, so there's no bank conflict. Okay? And the reason we can stripe it, we can interleave the banks is because we use the memory padding technique. Okay, so the memory padding means that you just waste some of the memory space in order to change the location of your memory on the memory banks. And in this case, you can see our problem is a 32 by 32 matrix transportation, but we waste one column. We add one column to our array, right, to create a 32 by 33 matrix on the shared memory. Okay, and then what happened is you can see, because you have 32 elements per row, so that the last column of the first row will roll it back to use bank 0, right? So that for the next column, for the next row of the first column, it will change to the red color, right? It will change to bank 1 instead of bank 0. Okay, all right. So as you can see, if we just keep right at the same time, still we only need 32 by 32 values, but we stored it on a 32 by 33 array. Then as a result, you can see we'll interleave the element on the banks, so that when if we try to read out the first column by a single WAP, all the threads will access different bank, and you have no bank conflict in this case. Okay, so this is what we call the memory padding technique. Basically, just referring to any in your code, you try to waste some of the memory in order to avoid bank conflict, or as we saw before, maybe it's try to avoid thread divergence, because you perform some additional unnecessary computation on a allocated memory, right? Instead of try to use a branch to identify whether it's a valid element or not. Okay, to make it rounded to a unit of 32 to avoid the WAP divergence. But in this case, instead, we try to make the space to be some number that's not evenly divided by 32, so that we can interleave the element on the banks. Okay, all right. So by doing this, then we can ensure the shared memory performance can also be optimized or fully utilize the bandwidth on the shared memory. Okay. Okay. So although also notice that although we waste the memory over here, right? It didn't introduce additional data movement or computation, because for our code, we just allocate a matrix with a dimension of 32 by 33. But in terms of our memory operation, for moving the data from the global memory to shared memory, or from shared memory to global memory, we still only require those data movement on the element that with data, right? So we still just require 32 thread operate on a matrix with 33 lengths. Okay, so we didn't introduce any additional memory access or memory operation. We just simply allocate additional or redundant or additional memory space. We waste the memory space, but we don't introduce additional memory access requests or operations. Okay. So that's why we can improve the memory performance without sacrifice anything besides the space. Okay. And of course, shared memory is valuable, right? The space is limited. So for memory padding, it is still a trade-off. It trades space for performance. So sometimes you still have enough space to, there still could trade off for other things, right? So still need to consider, okay? Whether it's not guaranteed memory padding or this, this usage can always provide better performance. Okay. All right. So finally, we will talk about linear address linearization, because as we mentioned, right, for band conflict and memory closes or closed memory access, if you have a linearized memory access pattern, then it's likely you can minimize those two problems, or you can maximize the performance on the shared memory as well as the global memory. Okay, and usually, as we have shown many examples already, right? You can do that by change how you linearize the address pointer that need to access for each thread to make sure they access continuous memory address, right? And in the order that is the same as your thread index. Okay, so I won't repeat that again. No, you probably should already know how to do that. So here we talk about another case that's less straightforward, but you need to pay attention to, right? So the case is if your element, your array you try to access has a structure, right? For example, say you are trying to manipulate a three-dimension coordinates, right? You have an array of a three-dimensional coordinates. In the past, if it's on CPU, right, just a naive solution, it's very likely you will declare your variable like this, right? What we call the array of structures, because it's an array of A, right? And you have n element, and every element is a struct, right? Is a struct that represent the coordinate of dimension x, y, z, right? So this is usually how we try to define the structure to store this kind of data, right? But again, you have to think about how the structure will be linearized, right, or serialized, placed on the physical memory. And what happened is you will linearize by the struct. So it will show like this. So you will have usually you will store a1.x first, and then a1.y, and then .z, and then store the second element, and then the third element. Okay, so this is the memory layout you should expect from this data structure. If you use a array of structures to store this data, then this is the memory layout on your physical memory. Okay? And this layout is not friendly to GPU. Okay? The reason is because since it's an array, right? You can imagine what happens is more likely that you are going to have a bunch of threads, and each thread will try to operate on one element at the same time. And they will operate, try to read or write the same dimension, right? The same element from the struct. For example, we probably try to read the data of X from every element first, and then maybe read the Y element from the Y value for each element, and then the Z element. Okay, so we actually try to read X together, and then Y together, Z together. And if the data memory layout is showing like this, then you will see that when you try to read X at the same time, the memory pattern is not linearized or consecutive, locate to each other, right? Because you have a stripe size of 2, right? And it will be worse, right? If you have X, Y, Z, A, B, C, D, E, right? Depends on how many elements you have in the struct, then that is your stripe size, okay? So this is not, not optimized, right? Because they have some striping memory access behavior here, okay? So if you try to read this data by by one dimension at a time, then what you want is this memory layout, right? So you put X together, and then put Y together, and then put Z together, okay? And this is what we call the struct of array, right? Because you will declare a single struct data type, and the X, Y, Z, they are list or array, right, within this struct. So for GPU and for the compiler, the result is you will linearize those data on the memory, like shown over here. So you will try to store the X value for all the elements, and then store the Y value for all the elements, so on and so forth. So that if you try to process the value of X at the same time, then you can see the address is linearized or consecutive, right? So at least for closest memory access, you should have the best performance, right? You should have probably 3 times faster performance than the memory pattern over here, or the memory layout over here. Okay. Okay. So this is just one thing you should look after if you have a array of a struct variable or data. Then you need to look at it more carefully, how the element of the struct is linearized on the memory, and see if you could rearrange the struct so that you can achieve even better performance. Okay, so usually struct of array can deliver better performance than array of structs. Okay. All right, so although it's less trivial for the programmer, but again, because of the hardware, how the hardware will function, the later case actually provide better performance. Okay. All right. Okay. So this is what we call the linear address linearization. You have to check the memory pattern and the memory layout to make sure you this really optimized without striping. Okay. Okay. So that's all the basic optimization technique we will introduce in this course, and I think that's pretty enough. It's pretty much enough for your homework and for the basic optimization. You should already, if you use shared memory, you use closed memory access, you avoid bank conflict, then in some degree, I'm sure the performance already can improve a lot. Okay? So finally, we will use example to show how we could apply all the techniques, probably not all, but most of the technique we introduce, and to show exactly how much performance can be achieved in a real case study. Okay? So as we mentioned at the beginning, right, it's usually not hard to port your CPU code on GPU, but it's really hard to get the best performance. And the example we show you, after a series of optimization, it can achieve a performance speed up to 30 times. So it's quite a significant improvement. Okay. All right. So the problem we're going to use here is the basic one, O reduce, right? Or reduction, right? We try to, given a list of elements, numbers, we try to compute the sum, okay? And of course, we try to explore as many threads or pair reason as possible. So again, we will use a tree-based approach to utilize multiple threads and do the reduction in a recursive way. So we can try to use as many threads as possible. Okay. Of course, you can see it's not perfectly parallelized, but still it's better than not parallelized, right? It's better than serialized computation already. Okay? But even in this simple solution, we already encounter some problem. Okay, so the first problem is actually this is one of the example we show before and explain before when we talk about the recursive parallel computation, right? And we know this is actually a synchronous computation. That means you have to finish the computation in the first layer or first level before you can compute the second level. There's a dependency between levels, right? So we have to introduce a global synchronization point across all the threads within the same level, okay? And this, unfortunately, may not be possible on GPU when the threads are thread across different thread block. Because remember, we said that between thread blocks, there is absolutely no synchronization mechanism supported by GPU, because we want to make sure every thread block can compute and can perform independently. Okay, so what happens is like this, right? So let's say if thread 1 and 2 locate on thread block 2, and the first thread also use 2 thread, right? So every thread block, let's say, only can support 2 thread, and here we need 4 threads, so we need 2 blocks. And as you can see, if you try to launch all the threads within a single kernel and using multiple blocks like this, then you can see there's no way we can synchronize between the threads on different block. So the thread 1 here cannot be synchronized to or wait for the thread 1 of the second block. So there is a synchronization problem here, and we cannot synchronize the two. Okay. So how can we solve that, right? So if we have multiple thread blocks, or we have a huge number of threads across blocks, and we need a global synchronization, how can we solve that? Okay. The solution is called the kernel decomposition. Okay. And the idea is that it's simply impossible to do that within a kernel. So we have to create multiple kernels, because we know that across kernels, there is a synchronization between them by default if they are executed on the same string, right, on the same GPU string, or submitted from the same CPU thread. Because those kernel, they will forced to execute it on GPU in a serialized manner. So of course, it's executed one by one. So there's a synchronization point between kernels. Okay. All right. So exactly how we can adapt that concept to solve our problem here. And you can see this is a solution. Okay, so we have many numbers, right? Then what happened is we can only handle assign the maximum number of threads to that number. For example, if here every block say maximum can only have 8 threads, then that means that for the kernel we launch can only assign a number for every thread block. Okay, and the number of blocks we issue, they can, as you can see over here, we can only process until the 3rd level. Okay, because we cannot have any synchronization between the blocks, the thread block. Okay, so we can launch as many thread block as we want, but at the end they can only handle up to the 3rd level. Okay, so since the result, you can see that within a block, you only need to perform synchronization across its own threads, right, within the block. So across thread block, there's no synchronization needed within this kernel. Okay, all right. So we basically every three level we launch a kernel, and for the fourth iteration or 4th level, right? For the rest of the iteration, we actually need to launch a separate kernel, right? And you can see that the idea is the same, right? We basically reduce the problem by 1/8, right? Reduce the problem by 1/8, and then we repeat this strategy again to decide how many blocks we need to launch from the kernel, until repeated this until we finally have less than 8 element, right? Then we can launch a single kernel with a single block to do the rest of the computations. Okay, so this is what we call the kernel decomposition. So we try to launch multiple blocks along the way, and make sure that the reason is within a single kernel, we need to make sure there's no synchronization is needed across the block. Okay, all right. So basically that is the idea. Okay, so just try to avoid synchronization across blocks, and for that sometimes you do need to launch multiple kernels instead. So that's why we call it as a kernel decomposition. Okay, so yeah, so by doing this, you can see that we can basically repeat the computation within each block. Every block, between block, there's no dependency. Okay, so the rest of optimization on the memory, we will only discuss on a single block. We don't need to care about the problem size anymore, or how many kernels we need to launch, or how many blocks we need to launch per kernel. They are irrelevant to our optimization, because the optimization always occurred on a single block, actually within the single WAP within the block. Okay, all right. So now let's look at the solution. Okay, so the first solution is a baseline. We will just illustrate by the picture, so don't really need to look at the code over here. But all you need to know is the first solution. All the optimization he did is to move the data from the global memory to the shared memory, as shown over here. Right? We have saw this many times. Okay. So the reason is, after you move it to shared memory within a block, the 3 iteration, you can access the shared memory instead of the global memory, right? So you can, of course, reduce the global memory access and improve the performance. So that is our baseline. Okay. But that code didn't carefully written. So as a result, this is the access pattern and the threads that is active from each iteration. And notice the element here, the data here already placed on shared memory. Okay, but even with that, the access pattern obviously is not linearized, right? It's striping, okay? And if you look at the thread index, it's also striping, okay? So there are a lot of problems exist, okay? So this is the performance for that baseline, okay? And the most important thing is this, okay? You usually don't really care about the time you measure because it's a relative measurement. So 8 millisecond, maybe things very fast, but doesn't really means it's optimized. You need to have a reference point, some bound, right? And one of the bound you could consider is the memory bandwidth, because memory is always the bottleneck. And so you can compute the memory consumption bandwidth from your program. For example, here, let's say the problem size is 2 to the 22 integer. So you can multiply this by 4, indicate how many data size you have to process, right? And you divide that by 8 milliseconds. Then that will give you how much data is processed, right? Is processed per second. So this is your data processing speed. And what is the speed of this GPU is actually 80 gigabytes. So 2 is very bad performance because the optimum bandwidth should reach 80, and you are not just 2. Okay, so it's pretty bad performance. Okay. All right. So why is so bad? First of all, you can see you have a warp divergence problem. Okay, because you can see that, for example, this is just we shrink down the scale. So let's assume each warp is only contain 4 threads. Okay, and over here you can see we only use 4 thread, right? 0, 4, 8, and 12. Unfortunately, they scatter across 4 warps, right? Because only thread 0 to 3 are within the first warp, and 4 is the second warp, 8 is the third warp. So we only need 4 thread. Supposedly, they should be all located in a single warp. So we only need use one SIMD processor to do this. But as a result here, you require 4 SIMD processor. And every SIMD processor, every warp, there's only one active thread within the warp. So you waste, you only use one-fourth of the computing power from the SIMD processor. So that's why it's very slow. Okay. So we can rewrite it somehow. Don't look at the code. If you want to look at the code, you can look at after. Okay. So what happened is after that code, you can rewrite it and make it to act like this. Okay. To change the thread ID that's active in each layer. Okay. And you try to make sure you use the right consecutive threads from a warp. So you can see here, we only require 1 warp per layer. So it's much better than the previous case. Okay. And the way to rewrite is change the code from here to here. Okay. You can try to look at it afterwards and see if this code will show this behavior. Okay. Okay. So after that, you can see the speed ups twice. Okay. Ideally it's 4, but you can see that we didn't fully utilize every warp in every layer. So at the end, it's about 2.3 times faster. Still quite an improvement, right? Okay, so we solved the warp divergence, but we didn't solve band conflict because this is on the shared memory, right? Remember, it's shared memory. So we want to access the data again in a linearized way. And this is striping. Okay, so it has a higher chance. And actually, in the worst case, probably is the if say the shared memory has only 4 bank, then this is actually the worst case because every 4 you have a band conflict, right? And this is also also a factor of 4. So this is a worst case for band conflicts. Okay. So again, we can try to rewrite the code and make it try to squeeze, right? Since we can write the data to any position in the array, so why not just write it to the consecutive position so that no matter how many banks it consists of the shared memory, if you can linearize it, you have the base you basically have the best chance to minimize the number of bank conflicts. Okay, so just try to linearize the memory access pattern. Okay, and you linearize in this way, of course, you can avoid or try to minimize the bank conflict, even avoid all the bank conflicts in some cases. Okay. All right. So again, this is how you could rewrite the code. Okay, and to avoid bank conflicts. And by doing that, you can see we achieve another factor of 2 performance speed up. And in total, you can multiply them together to reach 4.68 speed up. Okay. And finally, the last one, the last optimization we will introduce is reduce the number of threads you created or you needed, because you can see that as a matter of fact, even in the first iteration, we only require half of the threads to do the computation, right? We require 16 threads to move the data from global memory to shared memory if we want a thread to move one element only, because as you can see here, we have 16 elements. So we need 16 threads if we only let one thread to move one element. But in terms of the computation, we only need half of the threads from the beginning, right from the beginning. So one way is that you can see that we can rewrite the code, right? For the first iteration, when we try to move the data, we ask each thread to move 2 elements from the global memory to the shared memory. And when we move, we add them directly. So as a result, we will achieve the pattern as showing over here. But from the beginning, we only need 8 threads, not 16 threads. Okay, so we reduce the number of threads we require for the computation. And fewer number of threads means, right, fewer number of cores required, and you can launch more WAPs or more blocks at the same time. So you can see it can again achieve close to a performance of 2 speed up. Okay. All right. So now we reach 8. So how we can reach 30? There are a bunch of other optimization that's too tedious. And so just as a reference, basically you try to unroll the loops as we explained before when we talk about WAP divergence, right? If you can unroll the loop, then you can avoid some of the condition check central. And so there are other tedious optimization you can do to speed up by almost 2 from each optimization, and at the end you can reach 30. Okay. So if you wonder the actual code to reach that, we show you the complete code over here, but I not intend to explain it because they are very tedious, and some of the reason we didn't really explain in our lecture. Okay, so just a reference and some of the technique you could use to achieve the best performance. And the code looks really ugly, but the performance is optimized. Okay. All right. So that's all for CUDA. Okay. So we wrap up the our lecture for CUDA, and hopefully that's enough for you to finish your lab and your third homework. And from next lecture, we will move on to the final phase of our course. We are going to talk about the distributed computing. Okay. All right. Any questions?